Okay, good morning. I hope you all are having a wonderful Friday. As you can see, I am not here today because of a math competition. So you'll be watching this video for your notes. If at any time you need it to be paused, please let the substitute know. Um, so let's get started. Today we're going to talk about extrema. So we're going to talk about critical numbers, which I'll tell you what those are, and then absolute as well as relative extrema. Okay. So the first thing I want to talk about are relative minimums and maximums. This is something that you briefly discussed in pre-calculus way at the beginning of the year. Um, you may I can't remember if we've talked about them in this class, informally or not. Um, but a minimum or a maximum, a relative minimum or maximum, is going to be what looks like a hill or a valley. So if I draw this curve right here, okay, anytime we change directions, we have a minimum or a maximum. So this is what we would consider a relative maximum because we are changing from increasing to decreasing, creating a hill. This would be considered a relative minimum. Okay, we're switching from decreasing to increasing and creating what kind of looks like a valley. So I want you to take a couple seconds, maybe turn to your neighbor, but I want you to think about how would those points correspond to what's happening with the derivative. Okay, hopefully that was enough time, and I'm hoping that you recognize that here is where our derivative is 0. Okay. Now, this picture wouldn't necessarily be the only time we would have a relative minimum or maximum. I want to draw this picture right here. Could you say that this point was a relative minimum because we are switching from decreasing to increasing? Okay. So what would the difference here be as far as the derivative is concerned? Hopefully, you talked about how the derivative is undefined there. Okay, that is not a differentiable point because it is a corner. Okay. Basically, what I want you to gather from this slide is that our relative minimums and maximums are occurring where our derivative is 0 or undefined. These are what we call critical points. Okay. Critical numbers is when we have the derivative is 0 or not differentiable. So I like to say the derivative is 0 or undefined. Okay, so we consider that a critical number or a critical point. Okay, where we have these critical numbers, this is where we're going to have our relative extrema. Okay, or I guess I should word it as our relative extrema occur only at critical numbers. Okay. Now, I want us to just practice looking at a graph and picking out relative minimums and maximums. So we're going to look at this graph right here. Relative minimums and maximums occur basically when we switch directions. We can also think of these critical points where we have derivatives of 0 and undefined. So here we have a relative maximum at x equals b. At x equals c, we have a relative minimum. At x equals d, we have a relative maximum. And at x equals e, we have a relative minimum. Okay. Now, let's talk about the extrema part of this. Okay. Extrema. So if we have a point that is the absolute lowest point on our graph, okay, there is nothing lower than that point, then we call that the absolute minimum. Okay, so we have relative minimum versus absolute minimum. Okay, the maximum, our highest function value, so a point where there are no points higher than it, that is what we would consider to be an absolute maximum. Okay, so relative minimums and maximums are where we are switching directions. They don't necessarily have to be the highest or lowest point on the graph. It is just where we're switching directions, which is why we put that relative on there. Now our absolute minimums and maximums are where we are the at most, or the very highest and the very lowest. Okay. Now every graph is not guaranteed to have an absolute minimum or maximum. Okay, so let's talk about those different scenarios. I'm going to do a couple different graphs of y equals x squared. So here is the entire y equals x squared across this entire domain. Do we have any maximums, absolute maximums? No, because we extend forever in the positive direction. Do we have any absolute minimums? Yes, we have an absolute minimum of 0 at the point x equals 0. Okay, now I'm going to cut the domain from 0 to 2. Okay. Here, do we have an absolute maximum? We have a max of 4 when x equals 2. That's the very highest point on our graph. Do we have a minimum? Yes, we have a minimum of 0 when x equals 0. Let me change the piece of the domain we're looking at one more time. What if we looked at the interval from 0 to 2 where 0 is not included? Then we would have something that looks like this. Our maximum would still be 4 when x is 2. However, do we have a minimum? No, we do not have a very minimum point. We approach the coordinate 0, 0, but I cannot pick out a very lowest point. So in this case, we would have no minimum. Okay. One more time. Let's look at the open interval of 0 to 2. Here we have a graph that has no minimum and no maximum. Okay, we cannot identify a very highest point and a very lowest point on our graph. Okay, what was the point of me going through all 4 of those graphs? I want you to notice that as long as we have a continuous curve on a closed interval, then f is guaranteed to have both a maximum and a minimum on that interval. And as long as we're continuous and our endpoints are included in the domain, so we have a closed interval, then we will have a minimum or a maximum. Okay? So we need to figure out how to determine when we have minimums and maximums, absolute minimums and maximums. Okay, we are going to worry about determining whether our critical points are relative minimums and maximums later, but we do know that critical points have relative minimums and maximums. Sometimes those relative minimums and maximums could be absolute mins and maxes, but it just depends on our interval and the graph, obviously. So, in order to find our absolute minimums and maximums, we first have to consider our critical points in our interval. Okay, now I wrote the open interval because the endpoints we're going to worry about later. So the first thing we need to do is identify any critical numbers, because we know that is where we're going to have our relative mins and maxes. Okay. We're then going to evaluate each of the critical numbers so we know the function value, we know the height at that point. And we're also going to evaluate our function at the endpoint. So plug in A, plug in B. Okay. You're going to have a handful of points to compare then. You're going to decide which function value is highest. That is my absolute maximum. Which function value is lowest? That is my absolute minimum on that interval. Okay, so find your critical numbers and then evaluate your critical numbers and endpoints to decide which one is the highest, which one is the lowest. Remember, we are guaranteed to have one of each as long as we are in a continuous closed interval. Okay, so it looks like I have 3 examples to go through. Let's look at the first one. I want the extrema of f of x is 2x plus 5 over 3 on the closed interval 0 to 5. Now, please recognize that this can be rewritten as 2/3 x plus 5/3. So, what is our derivative? Our derivative is 2/3. To find our critical values, we need to figure out where is our derivative, either 0 or undefined. Okay, well, our derivative is a constant. This cannot equal 0, and it cannot be undefined. So we have no critical values, which means we just are going to test the endpoints. We need to test 0 and 5. When we plug in 0, we get 5/3. When we plug in 5, we get 3. 5/3 is our lowest number, so we say that's our minimum. 3 is our highest number, so we say that is our maximum. So we have a minimum at the coordinate 0, 5/3. We have a maximum at the coordinate 5, 3. All right, let's look at an example where our derivative is a little bit more helpful. So we have f of x is 2x minus 3x to the 2/3 on the closed interval -1 to 3. So the first thing we need to do is identify our critical values. We're going to do that by finding the derivative. So f prime of x equals the derivative of 2x is 2, and the derivative of 3x to the 2/3 would be 3 times 2/3 x to the -1/3. Okay. So I'm going to rewrite this as 2 minus, those 3's cancel, and so we're left with 2. X to the 1/3, I'm going to write in the denominator as a positive exponent. Okay. Now, before, I did not make you simplify your derivative. We have reached a point in calculus where it is important to simplify our derivative. Why? We need to look at where this is 0 as well as undefined. So it is going to be helpful to us if we can write this as one fraction. Okay? Not a problem. What we're going to need to do is make a common denominator. So this 2 over here, I'm going to multiply by x to the 1/3 divided by x to the 1/3. And then we would have common denominators. So our derivative is going to be 2x to the 1/3 minus 2 over x to the 1/3. Okay? In order to find critical numbers, we are going to need to decide when the derivative is 0 as well as when it is undefined. So first of all, when our derivative is 0, since we have a fraction, our derivative is going to be 0 when our numerator is 0. So this would mean 2x to the 1/3 equals 2. X to the 1/3 equals 1. Cube both sides to get rid of the 1/3 power, and we have a critical number of x equals 1. Now let's talk about where this derivative is undefined. Our derivative is undefined where the denominator is 0. So our denominator is x to the 1/3. We're going to set that equal to 0, which means we have a critical point of x equals 0. So what we need to do, we have two critical numbers and two endpoints. We have an endpoint of x is -1 and an endpoint x is 3. And then we also have critical numbers 0 and 1. So what we need to do with these four numbers is test them in our original function to determine which one's the highest, which one's the lowest function value. Okay? So when we plug in -1, 2 times -1 is -2. Minus 3 times -1 to the 2/3. That 2/3 power means the cubed root and then squared. So the -1, the cubed root of -1 is -1 squared turns to positive. So we end up getting -5. When we plug in 0 to our original function, 2 times 0 minus 3 times 0 to the 2/3, we get 0. When we plug in 1, 2 times 1 minus 3 times 1 to the 2/3 is really just 2 minus 3. So we get -1. And then when we plug in 3, we get 2 times 3, which is 6, minus 3 times 3 to the 2/3 means this 3 to the 2/3 would mean the cubed root of 3 squared, so the cubed root of 9. Okay, that's not something that we can evaluate. Okay, but we can put that in our calculator. I can already tell that that's going to be a negative value of some sort. Okay, so if you put this in your calculator, I believe you should get -0.240. Okay, so now we can make a decision. I see our lowest number is here, -5, and our highest number is 0. So that is our max. So we have an absolute minimum of -5 when x is -1, and we have an absolute max of 0 when x is 0. So if you wanted to write the coordinates, we have an absolute minimum at -1, -5, and we have an absolute maximum at 0, 0. Okay. Last example. Are you ready? All right. So we have a function, we have an interval. We know there's going to be an absolute min and max. We need to decide where. So the first thing we need to do is figure out our critical values, because that is where we would have relative mins and maxes. So let's go ahead and find that. Now, be careful. We have x times the square root of x plus 4. So first of all, we have a product. Second of all, don't forget to think of this as x times x plus 4 to the 1/2 power. That way we can use the power rule. Okay? So our derivative of x, derivative of x times the second function plus the first function times the derivative of x plus 4 to the 1/2. So power rule and chain rule, the derivative of the inside would be -1. So what are we working with here? We have x plus 4 to the 1/2 power plus x over 2, and since we have a negative power, I'm going to bring it downstairs so our power is positive. Okay, so we have x times 1/2, so that's why I have that 2 downstairs. We have 1/2. And then the negative power I brought down to the denominator to be positive. Okay, we are going to have to figure out where this is 0. All right, and so we need to make this one fraction. Not a problem. Okay, we need a common denominator. Our common denominator is 2 times x plus 4 to the 1/2. So I'm going to multiply this times by 2 times x plus 4 to the 1/2 over 2 times x plus 4 to the 1/2. So we end up getting 2 times x plus 4 to the 1/2 times x plus 4 to the 1/2 would become x plus 4 to the first power. When we multiply, we add our powers together. And then we would add it to our second fraction. So if I combine these two fractions together, our derivative, okay, stay with me here, we have 2x plus 8 in our numerator. So when we add it to the second fraction, we get 3x plus 8 over 2 times x plus 4 to the 1/2 power. So there's our derivative. Let's talk about our critical values. Our critical values, remember, occur when our derivative is 0, as well as instances where our derivative is undefined. So let's talk about our derivative being 0. Oops, derivative equals 0. There we go. Since we have a fraction, we are worried about where the numerator is 0. So this occurs when x is -8/3. We also have critical points when our derivative is undefined. Since we have a fraction, that is going to occur where our denominator is 0. Okay, so I'm going to divide by 2. When I square both sides to get rid of the 1/2 power, we get x plus 4 is 0, which means x is -4. So we have critical values at x is 0, or excuse me, x is -8/3 and x is -4. Now, does anybody have an issue with either one of these? if we go back to our original problem, our interval is only from -3 to 1. So while yes, x equals -4 is critical, it is not important to us in this particular problem because it is not in the interval. So right now, we are not going to worry about testing it to be an absolute minimum or maximum. Okay, next week, I promise you, x equals -4 will be important to us when we look at the graph in its entirety. But right now, it's not important to us because it's not in the interval. All right, so what do we need to test? Our interval is going from -3 to 1. So we need to test -3 and 1. And then we also need to test -8/3. So when we plug in -3 to our original function, we get -3 times the square root of -3 plus 4. So -3 times the square root of 1. Okay. When we plug in -8/3, okay, this isn't going to be the prettiest value. So let's go ahead and approximate that in your calculator. So -8/3 times the square root of -8/3 plus 4. You should get -3.079. And then when we plug in 1, times the square root of 5. The square root of 5. So our highest number is square root of 5. And barely our lowest number is -8/3 because it is more negative than -3. Okay, so we have a minimum, an absolute minimum at -8/3, -3.079. That's not exact, but that's okay for right now. And then our absolute maximum is going to be 1 square root of 5. So I'm going to give you a homework assignment, and I would like you to work on it diligently during the time you have left in class. Okay. Just keep in mind, for every problem that you're finding absolute extrema, you need to find your critical values and test those along with your endpoints. Okay. You're also going to have some problems where you need to identify the relative minimums and maximums based on a graph. All right, and so that's just going to be where you have those hills or valleys, those changes in direction. Okay, so here is your assignment. I hope you enjoy your Friday, and I will see you all on Monday.